Okay, so it's quite nice. We have this program first one. I was asked to talk about the Wigner distribution, and I take this as kind of more discussion rather than really a presentation about the Wigner distribution. Part of the reason is that I think many of you also agree with me that for this part, actually, although there has been a lot of activities, but still we are really in the early stage to really have a comprehensive picture and more rigorous theoretical framework and so on. So let me start with this. This one of the, I think, very nice plot. I think Max Steele actually put a lot of effort to have this cartoon in the white paper, and this has been in one of the highlights for the white paper in 2012. And you can see that we have Wigner distribution, and you have GPD, TMD, and so on. And I'm not going to go through all this development in the last 5 years or so, but if you are interested, you can go to much of detail of this reference. And instead, I think I would like to somehow maybe initiate some discussions, because there's still some many questions and for the Wigner distribution. I would like to highlight two of the important aspects. I think it's fair to say that part of this excitement in the last 5 years or so really started by I linked the Wigner distribution to the partonic orbit angular moment. And some of the here, and Barbara and Yoshitaka and myself involved to try to really rigorously and in QCD to link the orbital angular moment with the Wigner distribution. Basically, say orbital angular moment just the average of the R cross P in this language, and in particular, this actually to my view, that really solved the problem of the Wigner of the orbital angular moment in different form. For example, if you define Wigner distribution in terms of bilocal operator of the quark antiquark, and define this in terms of the Wigner distribution, and you find that in this language, the gauging connect these two fields is very important. If you just have straight line gauging, that's more kind of a convenient way to write down the gauging invariant operator, then you get the so-called G-summer orbital angular moment. But instead, you say, I want really to high energy experiment, try to study Wigner distribution in the DS or other related process, then you have to impose the so-called Lycon gauging. For that, you get a so-called Jaffe-Mannerheim spin summer orbital angular moment. So everything on this, in principle, we can have very clear definition for the different orbital angular momenta in the different spin summaries. So this one, I think, highlight for the Wigner distribution and the connection to the hadron structure, in particular for the spin summary of the quarks and the gluons. And another very interesting is that Yoshitaka, Bowen, and I was trying to kind of push forward to the small X physics. And I think my kind of rough idea is still, I think more or less true. You have very complicated projection for the Wigner distribution. If you take into account everything, X dependence, C dependence into account, and so on, it's very complicated. But in small X actually will be very, I still believe so. It's very much simpler, and actually related to the so-called objects for dipole scattering amplitude, which has been widely used in the small X community and also in ion community. So here you basically have two version 9 and sit in a different position, and of course you have particular X. That's your background of nuclear or whatever color glass condensate. And then these two positions actually will define the transfer momentum and also impact parameter. So that's actually everything encoded there. Of course, if you have spin effects, then you have the spin correlation that will be complicated. But mathematically, it's very simple in this way as small X. And you can say that, and maybe beyond that, it's very complicated. Anyway, so
is it known what gauge, what version of the gauge link the small x definition corresponds to?
Oh, this one?
Yeah.
Oh, so the first one, this is the gauge invariant operator. So, I mean, it's along the line column direction. So for that definition. Okay, so that's I just want to kind of give you some introduction why some of us actually interested in the Wigner distribution. So I will kind of briefly go through some of the recent activities, and each of them actually will I hope any people can jump in to have discussion on that. So I will kind of separate that into the theory part and phenomenology part. So Board and I, of course, you are all interested in how actually we are measured and what actually we learn from this Wigner distribution. So let me go to one by one. So first, I would like to point out Yoshitaka Hata and his collaborator are trying to push for this so-called Hasmi distribution. It's kind of Wigner distribution, and but with Gaussian smearing in transfer moment and Corner space. Advantage is that we know that Wigner distribution contains quantum information in the frame, so it's hard to have density interpretation or probability interpretation. But this one actually have because they have the Gaussian smearing between transfer moment coordinate space. K-curve, so you still have a kind of a probability interpretation. So that's in the kind of if you want to kind of sell this physics to outside, maybe it's also not bad to say that we do have some kind of probability distribution for the quark and gluons in the phase space in the transfer moment impact parameter space. So that's one direction. I mean, of course, there's many questions associated with that, right? Okay, another thing is actually very interesting that when Yoshitaka Hata, Bo, and I try to understand the small x in the small x context, and Zhenzhou also try to calculate this in the color glass condensing model. What we are trying to understand is basically once you have this impact parameter and also transfer momentum, and naturally you will have some kind of non-trivial correlation. And one of these non-trivial correlation is so-called cosine 2phi. That's the one immediate consequence if you have this correlation between these two, and which tells you that the Q curve, the transfer momentum and impact parameter correlate by the so-called cosine 2phi correlation. This the non-zero correlation will tell you some kind of interesting phenomena. And Zhenzhou actually went ahead to use a color glass condensing model, calculate this ratio between the so-called elliptic ground. We call it elliptic ground because it relates to some kind of elliptic flow phenomena observed in here ion collision. Jen actually went ahead to apply some kind of color glass condensing model, calculate this elliptic ground distribution, and also he found actually this maybe is quite sizable in the small x context. I mean, there's of course still model dependence, but many transpecies can be associated with that.
Feng, what is actually the general dependence on the right-hand side of this equation on phi?
Cosine 2phi.
Is it all?
What?
Is it all what we have?
No, you could have many others, but this will be one of that. It's very interesting, right?
So then this is not an exact relation.
Say it again.
The relation you write is written there is not exact.
Oh, no. I think this you could have many others, but I just want to highlight this is as this was symmetry, this was cosine 2phi is one of the leading terms.
And for this W, it corresponds to different GPTs of what those letters.
Oh, because no. Here, if you integral of the transfer of the momentum, you get GPD, right? So I will mention that later on. And if you integrate impair problem, you get a TNBs. That's the only constraint you will have. You know that they will have one-to-one correspondence. But at this level, I think you have, more than these two. I think Andreas have some of the expansions actually at the leading order.
It's probably infinitely many terms.
Many, yes, could be.
So, but one can show there cannot be a cosine phi, I guess.
That's true. Unless you have no rotation simultaneous.
It's probably related to the fact it's cool.
What exactly is this angle phi?
What?
What is this angle phi?
Phi is the estimated angle between the Q probe and transfer moment. So when you define the z direction, right, and then you have this cosine 2 phi. So somehow they have two maximum when it goes through from 0 to 2 pi. I mean, you cannot have one maximum because the efficient similar test, you cannot do that. But you could have two maximum, so that's why you have cosine 2.
So the phi is the angle between those two vectors transfer
Yes.
direction. So
Yes.
the function on the right-hand side are scalar.
That's right. So these two are scalar functions. The interesting part is, for instance, so when you do Fourier transfer, for example, you transfer Fourier transfer B probe into momentum transfer, for example, the TPD study. That also give you cosine 2 phi between transfer of the moment and moment transfer. I mean, this is just one of the velocity function, whatever. So they also have cosine 2 phi structure. Linear correspondence, we also have some similar. Yeah. So I may come back to this. So Mark already talked about this. I think it's very nice. I mean, it's now I have came out of this this long acronym for this paper, and they study the evolution. I think is very important. And the evolution, the conclusion I believe is that evolution is identical to the TMD evolution. My take of this is that if you look at the pseudo-curve double log, or some of the single logs, I think that's fine. But I still have question about, for example, you really look at the competing and answer dimension may be different. And what's the scaleness dependence? Normally, when you have Diglab evolution for the GPD, you are taking into account scaleness dependence. But in your calculation, you only consider.
We set psi to 0.
Oh, okay. Yeah. Okay. So you totally avoid that. Okay. And that's first step. So there's many issues, like I said at the beginning. Many of this physics, it's really just start to actually have some.
Say for non-experts, can you comment on the following aspect in a bit more detail? So this, if you look at the operator, the Wigner distribution is a very general operator. It's say some bilinear with a gauge link. So as you change the scale, it can probably mix with lots of other operators. So
yes.
What are you defining evolution as some kind of say, as restricted to a certain class of operators, or with what, say, with what operators does my operator mix if I change the scale? For example, can it be higher order operators like 4-field operators, or
so take
you don't have twist in here.
No. So that's part of the reason I say the pseudo-curve part, I think it's okay. In a sense, if you look at it, for example, you just look at the Q probe and B probe, right? And they are sitting to C actually equals 0, and the B probe is related to delta probe, right? So, but the TMD evolution is really concerned about when you have the different, for example, probe, then your transfer the momentum dependence will be affected because the ground radiation is partially, there's no complete cancellation between virtual and real diagonal, so that will change your Q probe dependence. So this is particular for the TMD.
And related to my question, do you define renormalization only in the sense to relate it to some divergences that you need to absorb, or there could be finite renormalization effects? As you say, suppose you look at your operator with some finite cutoff, you change the cutoff, you might get big finite renormalization. We know, for example, if we expand in twist, we know that twist 4 operators mix with twist 2 operators under evolution, and the coefficient functions are power divergent.
This TMD evolution is particular, so it's one of the so-called, because you have if you just follow for the naive TMD definition of Wigner distribution, if you use Nikon version 9, you have Nikon singularity. So by definition, you have to regulate that Nikon divergence.
That means you're really looking at the renormalization of this operator only in some very restricted sense.
No, no. For in the TMD sense, it's completely renormalized.
One comment is that in the case of orbital angular momentum, you can actually write down in terms of collinear. It's a particular projection of Wigner dispersion. So you can actually write down a collinear period, and it involves.
I mean, I understand for certain projections it might make perfect sense, but I'm just since you're promoting this object as a thing in itself, I'm asking. So suppose I put this up in a quantum field theory with a finite cutoff. And I change the cutoff. How does this object change in both?
So that's what the answer to your question. So once you change your cutoff, you'll have a circle effect, which is controlled by the evolution, which is exactly the same as TMD. Okay. So it's a well-defined object once you have regulated for the Nikon singularity. Okay.
So you could ask further questions. You could have evolution either in momentum space or evolution in position space. But this Wigner function, you cover both.
Yes. So that's
to what you guys say. I take the diagonal first and then do that.
Yeah. Yeah.
But
so that's
you can have both.
Yes, that's true. I mean, that's really the question asked Kristen this morning, how the delta probe actually will be involved. I mean, so far, what I can understand from what he's saying that the T dependence really coming from the X change, right? So the T dependence is not explicitly in your evolution equation. Am I right?
That's right.
Okay. I mean, it makes sense because that's really only related to the hydron states. It's not related to the operator itself, right? Okay, now I am going to the central question of my presentation, and also maybe what you guys really want to know. I mean, is any process actually we can start the Wigner distribution? We start a little bit, we kind of try to push forward. So we was trying to take a simple example and then try to push forward, right? So here's the process. We say maybe we can use that to study the Wigner distribution. I mean, this is not a really new process. Not only study this, and many other people also study this. But we are putting the new context, say that in his calculation, of course, he related to the collinear calculation with PPDs. But if we kind of relax that requirement a little bit, then we can say that this diffractive gadget, so you have photon counting and count Kugelbach pair, and Kugelbach pair will be hydronized into jet or other particles. And then you have the diffractive process. And then in this diffractive process, you could be sensitive to the so-called Wigner distribution in such way that the momentum exchange of this two gluon is done is a momentum transfer of the Q perp. That's actually the Wigner distribution transfer of the momentum. And of course, you have momentum transfer associated with nucleon that give you so-called improper space information. So just look at the kinematics. It looks like this process actually could be sensitive to the Wigner distribution, and that's our proposal. I mean, it's kind of it's not you cannot really avoid this kind of complicated process because Wigner distribution itself depends on transfer of the momentum and the impact parameters. So you have to have some process which which is complicated enough to have sensitivity to both of these. So that's one process we can think of at that time. Oh, this in this we study the electron production with Voltronic.
So electron production can do it. I mean, in photo production, it is okay in a energy limit, but linearization broken.
So that's what Yoshitaka later he continued with talk with other people and proposed actually maybe we can start also photon production. Maybe you have more.
What is the hierarchy of scales here? Why is it not
So hierarchy scale is foreign. So you have these two particles going out, and they carry large transfer moment, which is the same order as Q square of the virtual photon.
Yeah.
And the total transfer moment of this two is small compared to the individual transfer. That's the hierarchy.
Then why is it?
So the Q perp here will be I mean
why is it not collinear factorization? It might be an utterly stupid question. I mean, if your transverse momenta on the top are of the order Q, I mean, then
now this coming from the whole different TMDs actually. So this is actually in the so-called special kinematic region. You are sensitive to the transfer of the momentum environment. So in this particular transfer of the momentum region, you are actually sensitive to the Q perp in this because you are looking for
some small imbalance.
Yes, small imbalance. So this actually, Yoshitaka later found that if you take the photon because your Q square equals 0, you have even simple kinematics requirement. Let's back to this.
Can you go to larger X and
Yes.
maintain the picture?
I believe so. I believe we can still maintain this, but it will be much more complicated. And there, you have to take into account the X and C into account. In small X, you can do many approximations, so which will become much simpler. So here, the propagator only depends on transfer momentum. So that's much.
But there's no general rule which would forbid that this could also be studied in larger X.
Oh yeah, sure.
So this can be studied with project. The problem is only that there will be no collinearization. So
yeah, it's
okay,
not. I want to do TND factors.
Huh?
I want to stick to TND factors.
Linearization should work in fact. And another thing that we were not very happy about in this study is that this whole definition of exclusive jet production is a bit subtle, because of course you have the soft radiation and what exactly you do and how you show there is no soft
that's a very
from the ladder.
Yes.
That's
a very good question. That's very good
concerns with what accuracy can you actually find this imbalance. Yeah.
Oh yeah. This actually we can discuss it later in detail. But I can show you that I start talk to Yoshitaka Ata on this as well. This related to TMD resummation again. So tell me if I made some mistake in the following statement. So if you have soft ground radiation associated with jet, you can either factorize that soft ground into a jet, or you can actually calculate that soft ground. Of course, I'm talking about the still ground radiation in the digest system, not associated with neither here. If associated neither here, that would be very non-trivial. But I'm talking about some kind of ground radiation associated with the finest part. That should be okay.
There are for exclusive, for example, Sterman, not Sterman, is from Durham, I forgot. Jet algorithm. Precisely from Durham.
Yeah,
okay.
That's true.
So the integration is complicated. This is another stuff.
Yeah.
But
so what we are starting to look at actually, if I try to calculate the soft ground radiation associated with finest jet, that to answer question that this will modify the imbalance actually, but that's calculable. So it's basically the jet radiation. Yeah, there's some kind of Shulakov effect, but it will be but here it's not. So that's the one thing I want to address also, and Marcus think about. And the point of what we are trying to calculate still is the ground radiation associated with finance jet. That looks like a TMD, but it's not, because that ground radiation has nothing to do with the lower part of the Wigner distribution. I think that part is much more trickier. And if you have ground radiation here, I don't know how to deal with it.
What you really care is the balance of the jet.
Oh, that I can, yeah, that part I
that
think.
balance will also connect the bottom part. Because the ground radiation from each jet, they form the jet.
That's true. But suppose I have ground radiation and here, so how do you do that?
That's the way the part that imbalance of these two Q.
No, it's not.
Because
It's very
so what I say is that a moment the tree diagram, you put in the Q going up, Q per going up, Q per coming down.
Okay.
But once you have a radiation, then that part will break, that balance will break. And because you look for exclusive process, you look for inclusive process.
It's kind of semi-inclusive.
Well, what I know, I can say what I know. I know that there was this studies of inclusive production. In this case, this is employed by Bartels, I think, and somebody, that the big contribution comes if you have additional balloon emission from the LiDAR. And if you want, for the question is essentially if you want to define this exclusive jets experimentally, so that there was this idea, this diffractive pattern, if you go to events with large beta,
that's
then
beta. I see.
Somehow looked good, but I'm not sure that it can be done really at the level of so this was basically the definition, that the exclusive jets are called jets, because large rapidity gap is not enough.
Okay.
That was the point.
Okay.
Because everything, you will have this ground emission from the from the middle of the ladder, they completely change everything.
So if I take your point correctly, say that if I limit myself in large beta, I have a better chance to not be destroyed.
Yeah, this was, I think, if I remember, yes, that it becomes better. That was a way to separate what you call. But how exactly?
Yeah. So you're saying that the ground radiation associated with the LiDAR will contribute basically.
Deviate from the middle of the lander in the direction of this.
Yeah. Okay. That will change the environment.
That will change everything.
Yes.
So part of the problem could be avoided if one looks at dihedrons. But
dihedron is the same.
Then you have an additional complication
of the fragmentation.
You have additional transverse momentum, which makes it more indirect to address the transverse momentum on the lower part. Yeah. But in semi-inclusive DAS to study TMDs, we do exactly that thing.
I know. But the thing
in that regard, it would not be more.
It is. Okay, so. I mean, that's a whole totally different game. Okay, I can also talk about that. So once you include the transfer momentum fragmentation there, first of all, you introduce additional dynamics there, and second is you have leading double law. So basically, you have the TMD effect is much more stronger compared if I just looking for jet. So it's a subtle difference there. But I remember Nanami and Nets, and you both calculate the next linear calculation for this process, right? Did you also calculate next linear order? You don't remember, okay? So further, actually, Yoshitaka also tried to argue that UPC, so ultra powerful collision this morning, there's have been discussion on that as well. So you have the, for example, for nuclei, in his example, nuclei and proton collision, you could have a very strong photon flux from the nucleus, and then they have a diffractive interaction with the proton, and you observe finite jet. I think this is very promising channel, which actually we have data right now, maybe. So we just have to convince LHC people And Rick, it's a little bit difficult, and Star doesn't have any current capability to do that. But I think LHC should have some data on this, either from Atlas or CMS collaboration. And this could be one good example to study this. I mean, of course,
we can get Star on this.
You guys can do this too?
Yes, for like digest at low BP on the bar region.
But do you have Roman parts now? Or?
Yes.
Okay.
We do have Roman parts.
Okay, that's good.
Actually, we are thinking of upgrading the system to have better acceptance.
That's good. I mean, this can be, so this could be a first step to study this, actually. I mean, of course, there's always the issue, you have a photon, you will have resolved photon contribution that may have a little bit of complication there. But if we can follow what has been done from Hera experiment, or actually some of the LHC experiment also try to separate out the direct photon and resolved photon contribution. I think this is a good example to start with.
So there is an issue when Q squared goes to 0
yeah.
after factorization. So we have this. So when Q squared goes to 0, then there is an issue with the factorization rate.
But this really worked a lot on that. So if you have Q squared 0, then you only have factorization on a large energy limit. In a strict diffractive limit, there's still at least to be in double log, there is factorization. Otherwise, factorization is small.
Yeah, but
yes.
the next reading correction or the calculation to this process was computed recently by Sari and his collaborator.
And the next, you also.
But it's
The limit of Q squared goes to 0 was completely safe because the endpoint singularity is cut off by the KT. So if you, as long as
that will no problem. The whole problem right.
The problem is a collinear.
Oh yeah, that's right.
I see there are no collinear.
Okay.
If you can.
So then the only issue is to try to kind of resolve photon
what we
contribution.
found that there is this classical problem with Glauber region.
Okay.
But if you have it, no. Then they don't feature.
That's good. Then that's I think this is very nice.
So can you comment again on the hierarchy of scales? So you have the mass square of the diject, then you have the momentum imbalance, and you assume that mass square is much larger than imbalance square, and imbalance square is still much larger than lambda QCD.
Okay, in this,
you have two large windows.
In principle, yes.
Yeah.
But in this calculation, it's only leading order calculation. So the imbalance delta equal to delta per. So if you have additional ground radiation, that imbalance will be there. But here, because it's imbalance, it's just kinematics, the imbalance will be the total transfer moment for the two particles will be equal to total momentum change between the proton state, right? So that imbalance. If you have additional,
if you have no radiation.
If you don't have no radiation, so that's why you have a very simple case here. But in principle, T probably is much larger than the third. That's but you could have additional ground radiation, then that will generate imbalance between the two jets. That gives you additional scale. Right. I mean, I need to try it, right? I mean, this digest actually also is very helpful to try to understand the orbital angular moment. I don't want to go into much detail. Basically, try to form a kind of correlation between the total momentum transfer and one of the jet transfer moment. So that gives you sin phi asymmetry. If you have non-trivial spin for the proton, then that will naturally goes to the orbital angular moment of the grounds. And you can do the quark as well, but that will be much more complicated in that case. And this so that the previous couple examples really try to looking for digest in the diffractive process. And Andres and Janzo and with their collaborators, they came out with this very nice idea. Actually, we can study this also through double Juliet. So one virtual photon coming from the QQ bar ionization, another photon coming from another QQ bar. And the beautiful thing of this process, because the QQ bar actually coming from pion, so you have really very exclusive process, and you can, maybe Andres can comment more, but you can immediately find that the transfer moment information for final state to virtual photon, and their total transfer moment will naturally depends on the Wigner distribution for the incoming pion and also proton. So that's how you actually cover. I mean, again, so if you really want to study Wigner distribution, if you want to get more information for the hadron structure, you have to go to this complicated process. And this is just by nature, that's the way. And
your last point is very valid. It's the last point.
I mean, it's like I was trying to also, this maybe the data on tape at RHCO and Rick. I mean, this could be starting, and that's the first step to study. I don't know. I mean, did you talk to Compass people on this?
I once did, but the conversation was too long.
So I mean, the Young process. What's the relation of what's the invariant mass of the two gamma stars together?
Can be anything.
Can be anything. Is it
so what we require here is really that those virtual photons have a large mass.
Is it generally of order S? Or
it could actually be smaller, in fact.
Yeah. I mean, because if it's of order S, then I wonder why there's no handbag type contribution by the two gamma stars coming to the same photon.
If the two photons are, again, we talked about that, emitted from the same line, then you have a separation actually. It's similar to what people discuss for the GPD case. Pion, nucleon going to a single dialectal pair, and nucleon, when you have basically a soft contribution that is power suppressed. In realistic kinematics, one would have to see actually how this plays out.
But in perspective of separation, what do you want? You want to two virtual photons from one quark?
Yeah.
And what will you use the second quark?
So
there is no factorization. How is it possible? It's okay.
It seems. I mean, we know from other examples that, say, if you have exclusive annihilation into, say, for example, PP bar to gamma gamma, or gamma gamma to pi plus pi minus, these processes, where the invariant mass of the two photons, if it's of order S, then this is supposed to go through the handbag mechanism. This is the same type of factorization as, say, wide angle scattering, just cross channel, just like 90 degrees rotated. So
this is different. I mean, here you have really one parton coming like this, and the other parton coming like that. And
you don't have RFS.
But what you really want to exchange basically a quark in the T-channel.
This is like a more direct, right? I mean, just photon coming from quantum. Change dynamics to produce. I mean, if you think this is exotic, I mean, this one even more exotic, right? Double Chamani. And I don't think we need to go to much detail. We also try to study this double Chamani production and recently. So, I mean, everything I think is still in the exploration stage.
I mean, the count rate is larger.
Yeah.
It's way larger.
Yeah.
But apparently, and I didn't know that, it's apparently extremely difficult to identify it.
That's true. That's true.
That's a problem.
I mean, there's no good decay channel. I mean, the majority decay is hadronic decay, and I mean, two photons is too small.
They have seen eta C and LHC,
That's
but
inclusive.
I think it's the minimum is like a certain 3-particle final state, and there's tons of channels. They have different, very similar branching ratios. So apparently, this is very, very challenging to detect these guys.
Okay, so
what about high
There is one small difference for double JM compared to normal GPD. Normal GPD, you effectively pull out the one energetic parton and send back a soft one to. It's much higher probability that systems neutralize the color as a flavor they back the proton. But double JM, because kinematical constraint, you pull out a quark anti-quark, those have a large plus momentum.
maybe it's okay because
I mean, it's in meeting order, we can just address the average.
no, I think here the advantage is foreign, so it's coming from pion. So I
So
think
let's say for the proton side, pion side.
okay. I mean,
From proton side. For proton side, well, normally we have a diffractive process. You pull out active proton to deliver enough plus momentum to convert to whatever the host system wants to produce. Now you send back a factory soft proton to cover your color and the flavors to back to proton. If you take most of a kinematic process or diffractive process. Then, but in this case, because you require to produce two time-like hard virtual photons, so effectively you pull out the two larger momentum plus momentum proton, a quark, anti-quark, same flavor from your original wave function, and keep the proton state intact. So I think there could be difference in terms of rate.
It's urban region, so if the GBD gets suppressed there.
Yeah, I was thinking just not that conceptually you can have it, but in terms of rate, this could be much smaller compared to normal GPD.
We don't know, maybe, but
Because
we don't know much about the GPDs in the urban region.
Sure, but in this case, it's like you pull out the two very energetic, matched flavored full contact pair from your proton wave function, keep the proton state intact.
It would really be helpful if you wrote down the invariants and the regime, the asymptotic regime in which this is supposed to be valid. So you have your initial S, which is large, then you have the gamma stars, which can be large, and the invariant mass of the two gamma stars, which can also be large, and in addition, the invariant.
I think Christian, we did not put any constraint on invariant mass of the two gammas.
So I think
large S, large virtualities of both photons.
Then if you don't put any constraint on the two gamma star masses, we must assume that generally this invariant mass of order S. That's that. So your central mass energy goes into a priori goes into all final state particles.
That is not
equal.
I mean, they could actually go basically in the same direction.
They could, but it's a finite. It's a small fraction of.
But on the other hand, if you can choose this kind of matter of the two Neptune pairs, I mean,
I would be happy to choose any kinematics if you say what you actually choose. I mean,
for example,
not putting any constraint on a three-body final state is like.
The point is the following. So suppose that in the center mass spring of the incoming pion and the nucleon, right? So my rapidity of these two actually define. I mean, I want a valence quark contribution from proton. So
it's like if you do require valence, it's like a it's like a double scan.
Yes.
But problem you want to keep the proton intact. So the rate could be smaller.
Yeah, that's true.
One possibility to help you say, okay, I want the two photons going opposite direction, so you pick a larger one from one side, smaller from other side.
Oh, then Christian's Heisenberg diagram would be very important in that case.
If look at the different kinematic regions to see whether they can enhance the rate.
Yeah, I think for this, I think we just started a little bit. So I think there's many discussions. I mean, maybe this dead end. So, but in the last couple of minutes, I really want to talk about the what we actually learned from this. Let me skip this. I think once, and this back to the discussion we had this morning, and Jerry also really pioneered this part. So I want to have something really concealed, right? So I think the one thing we can study for the GPT is really proton size function X. And this actually brings me back to a very old plot I have. This didn't really happen to generate two plots. It's basically the transport profile of the grounds and the quarks in the imperial parameter, the B space. So this is the quarks, this is the grounds. And both they came from the fit to the Harrow data, DVCS. And this, you can clearly say that. Christian also mentioned about this. Harrow data show that the grounds actually typically in the range of the 0.5 to 0.6 fermion, while we know they charge really around the 0.9 fermion. So that's a reason Jerry also trying to study in total different contexts. But the one thing I want to emphasize, what the ground is really sensitive is color charge, because the ground doesn't carry any electromagnetic charge. But the quark actually carry electromagnetic charge. So DVCS, for example, quark contributing to DVCS will tell you about the charge distribution. But if we can find a process which tells us about the ground TPD, and which will be sensitive to the actual color charge of the nucleon or nucleus, right? It's actually very interesting. One thing I don't know actually from the ESA white paper simulation, and somehow this looks like contradictory what you presented this morning. You can say that a large X actually really is I mean, from my eyes, looks like really is larger than small X. Anyway, so I don't know.
No, this is not the normalized distribution. This has the information on the absolute gluon density.
I know,
so
but if you look at the shape, I will say, I don't know. Maybe I cannot say. Okay, anyway. But here is the very, very, I kind of, I don't know, you touched this morning a little bit. Let me just ask a question. What the asymptotic region of, I don't know, this morning I think somebody also asked, Andreas also asked, is there any separation will play a role? If we, according, I don't have the problem you showed this morning. So if I really study the color charge of the grounds, right? The ground radius as a function of X, and you show that this data show that the radius will increase with decreasing X. Is there any limit, or what is asymptotic region? What is asymptotic behavior for the charge radius for the grounds? I think that's one thing I don't know. And then I don't know if there's any, I think I asked you to talk about this question. Somehow there's no kind of in principle answer to this. I mean, if you relate to the Fourier bound, you say that would be close like log 1 X. Anyway.
I think we need to be more precise what we mean by like color charge distribution. In the case of the electric charge, we have an overall charge which is distributed.
Yes. But here you're saying the ground is
the primary thing we measure is the gluon density per transverse area. So that's
okay. I mean, what Jerry plot here is the charge distribution, of course.
Yeah.
Transfer charge distribution.
Yeah,
and this can be. I mean, he plot started this with form factor. Yeah. But you can do the same thing for the ground. I mean, you have the ground.
That's what I'm saying. What it gives you is the transverse density, the density of gluons per transverse area, per X per transverse area.
That's charge density. Color charge. Because ground carry color, right? I mean, this quark also carry color, of course. So the ground also interacts.
Not necessarily, because it's not related to a global charge. I mean,
it's not really. Then what are you talking about this?
For example, I mean, with the color charge, that's that's a property, if you like, of the valence quark GPD. So it's quarks minus anti-quarks. If you change the scale and you radiate an additional quark anti-quark pair, it doesn't change the charge because you create quarks and anti-quarks in equal amounts. So then you can say I have a certain charge density per transverse area, and I change my resolution scale, and I change my normalization scale, and because that charge is conserved, it doesn't do anything to that. It's not the case with the gluon density. If you change the scale, it radiates, and you just get more gluons.
I know.
So
we know. That's why, because they say
QCD
is not variant. QED is a variant. So that's answer your question. So that's why it's actually interesting to ask this question, right?
I just would be careful calling it a color charge density. It's I would say it's a gluon density per transverse area, but
I
how
think
to go from there to a proper color density, that's it needs to be discussed.
These things go into valves because the electromagnetic current is conserved. The gluon express valves, I think that's the difference.
That's true.
You certainly have a lot of color charge locally per transverse area, but in a more like fluctuating sense, not it's not necessarily the right path.
You can always define the effect radius of gluon density, effect rate proton in terms of gluon density, not the color. I agree, because there is no elastic color form factor. But in terms of density,
absolutely.
Well, wait a second. I think that we can still define elastic ground form factor. This is how you define GPD grounds, right? I mean, you say,
when I say elastic
that's a color,
gluon current, single gluon, like electromagnetic, elastic electromagnetic form factor as a current photon, electromagnetic.
I understand. I mean, I don't know. I think this
in the sense
maybe I will have to think more on this. But if I just do analogous for the quark with grounds, what's the difference for your GPD quark and GPD grounds?
Including analysis dimension.
Yeah, but this thing could be also made scale dependent because you could. This is integrated over X. But you could look at a specific X and be dependent scale evolution as well.
Yeah. So charge experience could also have resolution scale dependence. That's true. Yeah. I don't know.
Yes, right. You define the color charge. It's not agent variable. Like agent non-invariant things. Of course, you can say that we implicitly meant some heat, but then that will not use the terminology. And if it's a ground density, okay, I understand. But if you're starting writing me,
I see.
Non-invariant operators.
Okay, that's good point. That's good point.
In that sense, I mentioned earlier, you cannot define form factors. A matrix sum of proton to proton with single gluon current.
That's
right.
right.
You define that when you find proton cannot be proton anymore because gluon can come. And gluon, of course, can be. But you can define the density in a two gluon.
That's two gluon density. Yeah, I don't know. I'm still, maybe I have to think about it again. So, I mean, this, okay.
I think if you
we should call it ground density. But it's not as fancy as the color.
Or if you want a physical object, it's
okay, it's not getting right.
It's the dipole cross section at a certain impact parameter. You can imagine preparing a probe, some kind of onium with a small size, and you poke it through your nucleon at a certain point, and then that probe will probe the local gluon density, and then you can make that like almost a physical quantity.
Yeah, I agree. I call it a ground density. Yeah. Anyway.
The whole point is that probes have to be better.
That's true.
Probe has to be covered. Otherwise,
So what is color charge then? What is color charge? I mean, CGC always using this terminology as color charge.
In the McLaren Hugo-Pollard model, it's, we talk about the big parameter called mu squared, which is basically the color charge squared per unit area.
Color charge is squared.
That can be defined.
Oh, yeah, that's a nice one. Color charge is squared. Wow. It's same as a ground density.
I think it's just the value of a minimum.
So I mean, of course, I think everybody will agree that. So what we are starting here is somehow related to charge, electromagnetic charge, right? And it's still different, right? So yeah. I mean, of course, this is my last slide. This is borrowed from Jerry. Size doesn't matter. So yeah. Okay, that's what I want to say.
As you mentioned, Jerry, just a new paper by Christian. Size doesn't matter. How you analyze it, the proton radius.
Yeah, this is a long story. I don't want to get started.
Jerry already wrote like dozens of papers on this.
Yeah, I mean, I saw Christian present that. And I looked at the paper, but I also saw the presentation. I guess it was one thing. I'm worried. There are many different determinations. I mean, you guys may know more than me. People from JLab, maybe you talk to PRED collaboration and come out with your results. I mean, my opinion is that many different people have used the same data and they get widespread in radii. And I don't want to, base my physics determination saying I like this person better than that person because I think he's smarter. So the data set as it exists now does not support an answer from electron-proton scattering. The puzzle came from hydrogen spectroscopy, and there will soon be some news, I think, that will resolve that. I mean, I had to give a little. I think within a year it'll be known. It'll be known relatively soon, but certainly the PRED experiment, provided they get accurate data that could be more definitive. However, what I saw also in Palm Springs, which was at the end of May, I was not convinced by what they had then. Maybe by now things progress. They don't know. Tanya may know more than I do about this, but I think they're going to make an announcement in the DNP meeting in Hawaii.
The special symposium.
Yes, and I'll be talking there, but they'll be making an announcement that that's what they do.
So you mean that they're already generating excitement for their announcement?
You already know what they will announce?
No,
no.
Which way? Which way to go? Is this way or this way?
I mean, if I were betting money, and I don't really know because I try to find out from various people. They wouldn't tell me until some of them won't say until they're published. Some won't say until they go to Hawaii. I would bet. I would put my money on closer to 0.84.
84. Okay.
And I think
that's how you call your announcement. Otherwise, it's just.
I'm not going to make an announcement. I'm not the one. I didn't do the PRED experiment. I just knew atomic physics experiments. Which are really the key things, and that really involves years and years of hard work. And just reading. I'm a spectator, and I mean, the result I always was afraid of, and I'm sure I talked about this at JLab, and people notice what I always worried about is that error bar on hydrogen spectroscopy is a little bit too small.
Mm-hmm. Yeah.
In other words, well, it's kind of depressing if you think the most boring. It's not always true that the most boring explanation is the correct one, but this may be one of those things.
Yeah, it could be.
More than I want.
I mean, it could be. I mean, they just boiled down this one. I mean, if you look at the orange data, it's wide range.
Yeah, I mean, there's a long discussion during that. People have been hearing talks all day, including you. I'll talk to you about it. Sure.
Can I ask about the Dirichlet process? So that's sensitive to the Wigner distribution, but not to GTMDs. What?
Oh, GTMD is Wigner distribution. It's the same thing.
All right. Okay.
So it's just you know, different people have different terminology. You know.
Right. That
Yeah. Sorry about that. You know, series want to have their own thing.
Feng, I think you skipped something about deep virtual cotton scattering and small x. Would you like to say a few words about that?
Not too much, but then on one thing I just want to say maybe this cosine 2 phi. This we call inhibited ground distribution or inhibited GTMD actually also contribute to the DVCS cosine 2 phi. So basically relate to the so-called helicity general ground distributions. So cosine 2 phi symmetry DVCS will also kind of provide information on the Wigner distribution, if you wish, or inhibited ground distribution at small x. So, yeah, that's kind of cool. Yeah.
The beta hydra can also give this cosine 2 phi. So
What
could be?
Oh, beta hydra? Okay, yeah. I mean, that's true. But we just assume that at small x, DVCS is dominating.
I wanted to come back to the question in what terms we should be talking about the Yuan density or the color charge. For
okay, cool.
And I mean, as Volodya said, I mean, we need a color singlet probe.
Yes.
Okay. And there's actually a very natural definition. If we look at if you consider the dipole hadron scattering amplitude, so we can prepare a dipole, which overall color singlet as an almost mathematical object. You can imagine it emerges from a virtual photon with defined virtualized, so it's color singlet, and then it couples to the gluon density in the target.
Mm-hmm.
And we can look at that, at the strength of that coupling in impact parameter, both as a function of impact parameter and as a function of the dipole size, which sets the scale.
Yes.
And then actually, one can represent that scattering amplitude in the same way that I described this morning, as one does for the proton scattering amplitude in terms of what's called a profile function. Mm-hmm. Which has the advantage that one can easily identify the degree of blackness of the target and the unitarity limit. So then it's actually a very nice kind of summary quantity. One introduces the gamma function for the dipole hadron scattering. Mm-hmm. Gamma going to 1 corresponds to the black disk regime, and that's the end of it. I mean, it cannot get any blacker than that. And I mean, this was actually suggested in these works that I quoted this morning with Frankfurt Strittmann to think of high energy scattering in this way. I think it's a very natural representation, which in some sense it quantifies the gluon density per transverse area, including like scale dependence, but it does so with a quasi-observable color singlet probe, which has the advantage that you have an intuition for it. It's when gamma close to 0 means your target is transparent, this color transparency. Gamma close to 1, it's black disk limit. So if gamma becomes of order 1, it means that nonlinear effects become important. So
you're talking
it's
about
very intuitive and
dipole, no momentum transfer to the dipole, just go straight. Or
yes, yeah. So it's basically like you prepare a dipole.
Right.
The dipole size is much smaller than the hadronic size, so you can imagine it emerges from some virtual form.
Its width is not changing. It's not going to.
It's like I don't know.
Forward,
it's
doing forward scattering.
Yeah. No, you can do real, say, elastic scattering. You can transfer some transverse momentum between the dipole and the proton, and then you can represent it in exactly the same way as any high energy scattering amplitude in terms of this profile function. And
right, but then in that case, if the momentum transfer so Feng just talked about the case with this guide jet going back to back.
That's it.
And your picture is more or less that it's going it's diffractive and more or less going straight with maybe some small angle.
Like the it's basically the iconal version of it.
Right. So then you have multiple scattering on the target in that case. If it's iconal, you have multiple scattering.
Exactly.
You have different powers. You have powers of the gluon density.
Absolutely.
Powers of rho squared.
It's all included in the quantity gamma.
It's all included. So you don't know what it is.
So that's exactly the point. It's the sum of all these nonlinear effects. But the point is that's a physical quantity. It's a cross section, and we know it can't be blacker than
right.
It can't be blacker than black. So
I mean, that's what the small x people use. In the small x limit, you can use the picture. If you go to large x, you cannot use it.
The point that I like is you can use that picture independently of the dynamics that generates a small x gluon density. You can use that picture for in connection with D-gap evolution, for linear factorization. You can use it in connection with DFTL. You can use it even with like
only at high energies.
Only at high energies.
But where really your dipole basically the dipole width stays constant over the time of the interaction.
Exactly. But the point is the result of all these different approaches to small x dynamics can be cast in the same function, gamma, which is like the opacity of your target for a dipole of certain size, and then you can start comparing them at that level. And it's a physical quantity, it's gauge invariant, and it's a cross section.
Yeah. I mean, they boil it down to the GPD, I think. I mean, originally I used the transverse profile, but I just want make it more fancy, say this car charge. But you guys say this is not good. The transverse profile also nice. Right. I mean, essentially it tells you how the gluons and quarks distribute inside nuclei. Right.
So if you integrate over everything for quarks, you obtain the charge.
Yeah.
If you integrate over everything for gluons, what do you get?
I don't know.
It's like the ghost.
I think it will be like what Christian talked about this morning will be like inelastic profiling. Right. So you get a very large area. That's how you actually the total cross section will increase. You never bias cross section.
I think what Peter is asking you.
Yeah, that's what I mean. Yeah. So you'll see like elongate the profile function. It's not your small configuration, your hard process. It really solves. Because when you do the integral, you take up more and more small configuration. I don't know if it's converging.
And X times?
X times integral is converging, not without X, right?
Would this tell us? Would this be a contribution to this A of T? Or to the
energy?
Yes, A of T. Yes. If you Fourier transform.
principle, the gluon, whatever gluon density you define is a gauge-dependent concept. What is subject to physical limits are cross sections, like a dipole hadron cross section cannot more than a black disk limit. The gluon, say PFKL, the D-glab gluon density, it can grow forever and ever. At small x, there's nothing wrong with that as long as you don't associate a cross section with it.
Yeah, but it is a well-defined contribution to the momentum. But x times.
You basically trace every.
In the second moment, these small x contributions are killed by x, and then go back to the evolution of the local operator.
No, I'm just asking if there's some nice sum rule for this.
That's a good question. I mean, if you integral b and k probe and x, you get momentum contribution, right?
Yes.
Now, if you integrate x and k probe, then yeah, I don't know. For the quark, we know it's charged, right? For the ground, I don't know. Should be finite number.
Could you explain one thing in this definition of the Wigner function in terms of this, iconal lines or U correlators, because it's not so obvious in the original definition of the Wigner function. You have, say, the second quantized quark field at two positions.
I don't have that here.
And how is that?
I'll try. Let me try to explain that. Okay. So
how is that definition related to what you have on the next slide in terms of this?
No, I don't have the spirit here. So suppose you are. So if we talk about the ground, right? So this would be FF, right? And then you have Fourier transfer this into to get the Wigner distribution, and then you have this. We're talking about Nikon gauging here, right? So in the small x region, you basically transfer one of the gauge link associated with F by doing this manipulation of derivative on the gauge link. So if you do the derivative on the gauge link, you get F times the gauge link, right? So that's how somehow you relate to the small x part. So, and of course, in terms of really ground distribution, you need to do the derivative respect to this two version line. So version 9, two version 9 here just give you dipole amplitude. But in order to get ground distribution, you have to do the additional derivative on that. So you have two version 9. If you do one of the derivative on this, one of the version 9, you get F times the gauge link. And another one is F times the gauge link. Then they can combine to get F plus gauge link. Yeah.
It's not like you think of fields sitting at the end of this gauge.
No, it's not. So you on top of that,
you in the transverse derivative.
Yes, transverse derivative, and also you take a small x limit. I mean, nice thing about actually, I already talked about this mathematically. But I mean, he actually literally used this business distribution in his paper. Everything is already had this idea many years ago. Okay, anything else for the discussion this afternoon? Quite an interesting discussion, yes.
Yeah, maybe some philosophy.